All right, guys, welcome to Unit 4. So we're going to go back to derivatives. We started off the year by talking about derivatives and what they are. You guys might recall that a derivative is the slope of your function at one point. So for instance, if I had a line like this, we would find the tangent line touches a graph at one point, and the slope of that tangent line is the derivative of the function at that point. Okay, and so that's what a derivative is. It's just something that tells you what is the instantaneous rate of change. Okay, so just bringing back some vocabulary for you. A derivative is an instantaneous rate of change. It's written like this. It can also be written like this. It's the slope of your tangent line, which is a line that touches your graph at one point. Those are all things that we talked about at that time. And so now in that chapter, I gave you guys some magical things that would just get you answers. So for instance, if we had this function here, you guys know what the derivative is now, right? The derivative is 2x. And so what this is a formula that can tell you the slope of your function at any point. So if you wanted to plug in 1, then that would tell you what the slope of your function is at x equals 1, and so on. But what I said we wouldn't talk about back then, we are going to talk about today. What I didn't talk about back then is, how the heck does that even work? Why does that process of putting this exponent here up in the front and then taking 1 away from it, why does that give you a formula that actually tells you the slope of your function at any point? Why does that work? It wasn't just voodoo magic. Somebody actually came up and found out that that works, okay? And so that's what we're learning today, is where all that stuff comes from. And it's called the limit definition of a derivative. So really all I've done so far with derivatives with you guys is I've just told you ways to get the answers, but not really why those ways work. And that's what the beginning of Unit 4 is going to be all about, is why those little shortcuts work. In fact, the extra credit that I'm going to give you guys, if you're interested in doing it over the week off that we have, I'm going to let you see why every rule we've ever learned works. We're not going to do that in class. We're just going to do it to a few different various functions, but your extra credit is basically to prove why every rule that we've learned so far works. So let's go ahead and get started. So we call this the limit definition of a derivative. And now you guys are going to think to yourself, all right, Mr. Bailey, so why are we learning this new way to find derivatives if we already have a way that works? Well, you're right in one thing. We are going to always just use the shortcuts, really, okay? But the reason we're learning this is because sometimes there are some, first of all, this is what math is. You learn why things are what they are, right? But secondarily, for your AP test, they can actually ask some questions where you have to know this stuff. So that's why we're going to learn it. Let's go ahead and we'll jump in. So the first thing that I want to do is I want you guys to pause the video here and I want you to sketch this graph, okay? All right, so now that you've got your graph sketched, I'm going to draw some things on here, but I don't want you guys to write it yet. I will have you guys write some things on your graph in a minute, but for now I just want to jog your memory with some old and familiar things. All right. So let's go ahead and first of all remember this. This is a line, a straight line. Let's call this red line here. We'll call the red line f of x, okay? Now this blue line, though, is a linear function. It's a straight line, and it's going from here to here. And that's what we call a secant line. A secant line is a line where you're connecting 2 points on your curve together with a line, all right? So let's go ahead and call this first point here x1, y1. And let's go ahead and call this point over here x2, y2. All right. Now, x1, y1, let's look back at that point there. This point is x because it's over that far on the x-axis, so the horizontal distance from 0 there would be x1. And it has a y1 because that's the height of that point, which would be a height of y1. In the same way, this point over here, x2, y2, has a horizontal distance located at x2 and a vertical height of y2. Now, as you guys might recall, the secant line, once again, that's the blue line that connects two dots on our function, f of x there. The secant line has a slope also, right? And the slope of that secant line is what we call the average rate of change. Now, once again, you're not writing this stuff. I just want you guys to pay attention with me. But the average rate of change is basically just the slope, so I'll put m, of the secant line. And you guys know how to find the slope of a line. It's rise over run. So we want to find out how far up did we go to get from y1 to y2. In other words, how far apart are these? What's the rise? Well, you would do, to find that, you would do y2 minus y1. And then you would find the run. That would be the distance between your two x values. How far apart are your two x's? That would be my bigger x value minus my smaller x value, x2 minus x1. And so as you guys know, slope is rise over run. My rise is y2 minus y1, and my run is x2 minus x1. So the average rate of change of my function, f of x, is the slope of this secant line, which is y2 minus y1 over x2 minus x1. And we learned a symbol for these also back in Unit 1. We call that delta y, and we call this one here delta x. Delta y and delta x just means y2 minus y1 or x2 minus x1. So another way we could write our slope is like this. Okay? So this is all review of some basic stuff, but this isn't what I wanted you to write just yet, because I'm going to write some new stuff on this graph that I do want you to write, and that's the stuff that you need to really make sure you know. But these first few things that I wrote will help us understand what I'm going to write now a little bit better. All right, so let's go back now to the beginning here. So I'm going to rename this point. Instead of calling it x1, y1, I'm just going to call it x. And as you guys know, since that point's on the red line, the y value is equal to the function's value when I plug in x. So instead of putting y, I'm going to put f of x. Okay? So in this case, that's x. And instead of calling that y, I'm going to call that f of x. Now this is where I would like you guys to start writing with me. Okay, so let's go ahead and label that point x, f of x. That horizontal distance from 0 there is x, so we're going to put x on the x-axis there, and then the vertical distance is going to be at f of x. All right, now my next point is going to be located over here, right? But I'm not going to call it x2. Now you guys might recall that we called this distance, what did we call that distance from there to there? Well, we called it x2 minus x1, right? But what else did I call that distance? I called it delta x. Okay? So now I'm going to give you guys a new way to name this point right here. I'm not going to call it x2. I'm going to say, okay, well, I start here at x, and then I'm going to add this much to it to land here, right? So we start here, we add this much, and we land here. So in other words, that point will be x plus delta x. My starting point plus the change in x. So we start here, and we add this much more, and we land there. So that point is going to be x plus delta x. I want to write it a little bit prettier, though. I don't want all these extra boxes and stuff on there. But so this point is what I'm going to call x plus delta x. So instead of calling it x2, it's basically my starting point, x, plus the change, which is delta x. And that puts me at my second point. So now, if I want to label this point now. If I were to label this point, I would call this the x value x plus delta x. And if that's the x value, the y value will be the function's value when I plug that into it. So instead of y2, I'm going to call it f of x plus delta x. All right? And that means that this y value right up here is going to be f of x plus delta x. All right. Now, let's go ahead and we're going to rewrite our slope formula here. Okay, so remember how it's y2 minus y1 over x2 minus x1? Well, in this case, with these letters, what would it be? All right, now, at this point, I want you to stop writing, and I want you just to watch, but I will have you resume writing in a moment, okay? But first, let's go ahead and let's fill in our formula. What would be y2 minus y1? Well, that would be f of x plus delta x is my y2. And what's my y1? That would be f of x. So there's that. Now let's do the bottom. What's x2? x2 is x plus delta x, right? And what's x1? It's x. So there's my formula. Now the reason I didn't want you to write this because I'm going to simplify it a little bit. You guys see how there's an x here and a negative x here? Well, those are just going to cancel each other out. All right, so really I'm just going to rewrite this a little bit as just having the delta x on the bottom, and that's it. Which makes sense, because remember how earlier we said that x2 minus x1 was delta x anyway? So there you go. All right, so this is what now you guys can go ahead and write down that formula, okay? Now that is another way to write the average rate of change of your function, okay? That's another way to write the average rate of change of your function. But this little expression here has a special name. It's called the difference quotient. Now, that's what we call it in calculus. It's called the difference quotient because we're subtracting our y values and our x values. And it's a quotient because it's a fraction. So it's just a fancy word for slope, okay? So we'll go ahead and put our little definition there, but that's the difference quotient. It's the slope of our secant line, or it's our average rate of change, okay? Now, as you guys might recall, calculus is all about finding not the average rate of change, but the instantaneous rate of change. And that means that instead of finding how much did we change from this point to this point, instead we want to know how fast is that function changing at only one point. So in other words, I want to find the slope of a tangent line, which looks like this. It just touches the red line at one single point instead of two. So how can we do that? Well, you really can't, all right? But well, you can and you can't. So let's bear with me here. You'll see what I mean in a minute. But here's what I can do. Here's what we did last time. Last time when we did this, we took this point here and we brought it closer and closer and closer and closer to this point. And as you guys can see, the closer I get, the more that looks like a tangent line, doesn't it? And when this purple dot here actually lands on top of that black dot, then it's going to be a tangent line. All right? Now, let's go ahead and see what do we need to do that. Well, if I'm doing this, what's happening is I'm making the purple dot become closer to the black dot, right? So what I'm trying to do then is I'm trying to bring this dot here closer in. And by doing that, that makes my delta x, the distance between the 2 points, smaller, doesn't it? Every time I bring this thing in a little bit closer, the distance between the 2 points is shrinking. So like if I were to put it there, for instance, now look at if I were to put my delta x back on there. My delta x is much shorter now. See how small that distance is? Formula still works. It's just that now it's just the delta x is smaller. The distance between the two points has shrunk. Now, the point here is that I'm trying to bring this purple dot in as close as I possibly can to here. Now, that's really close, right? That's almost a tangent line. But the problem is those two dots have not become one yet. but it's still really close. And so that's whatever the slope is of that blue line at that point. Well, at that point, that's going to be pretty much the slope of a tangent line because it's so close. But we have a problem. As soon as you actually try to land on top of that point, did you notice my blue line just disappears? The reason for that is my computer doesn't understand, because this is on Desmos, the computer doesn't understand this. And the reason it doesn't understand that is because as soon as those 2 points become 1, what does delta x equal? As soon as I put that purple dot right on top of that black dot, what does delta x become? Remember, delta x is the distance between the 2 points. But if I take those 2 points and put them together, what's the distance between them? It's 0. Why is that a problem? It's in the denominator here. The slope of that blue line has a delta x on the bottom. And if I let those 2 points become 1, then my denominator becomes 0 and it's undefined. So that line cannot exist at that point. So what we do is we can't find directly what that slope is. But what we can do is we can let delta x, even though we can't let delta x be 0, we can let delta x get closer and closer and closer to 0. Is there a concept in this class where we've talked about letting something get closer and closer and closer, although it can't really equal it? Well, yes, there is. We just finished a whole chapter on it. It's called limits. So what if I were to take this difference quotient and find the limit of this difference quotient as delta x approaches 0? If I let my delta x approach 0, then my slope of a secant line gets closer and closer to a slope of a tangent line. And my slope of a tangent line gets closer and closer no longer to an average rate of change, but to an instantaneous rate of change. And we have a symbol for that, don't we? F prime of x. So this is what we call the difference quotient. Okay, so I want you guys to know that. But this is the limit definition of a derivative. Whenever you take a difference quotient, a basic slope function, and you find the limit of that as the distance between the 2 points approaches 0, in other words, the 2 points become 1, you end up with a derivative. And that's what we call the limit definition of a derivative. Okay? And we're going to be using that on every problem that we do today. All right? So that's our introduction to the lesson. Now, what we're going to be doing for the rest of the day is we're going to be finding some slopes, some derivatives, but we're not going to use our old shortcuts that we know. Instead, we're going to use the limit definition of a derivative. So let's go ahead and begin here. And here's my function. All right. Now, if I ask you guys to find f prime, you're going to know the answer really quick. So don't write this, but just watch with me for a second here, and you guys answer the question. Can somebody tell me what is f prime? I hope everybody can. F prime is just 2. Okay? The derivative of this is 2, and the derivative of this is 0, so we're just left with 2. Okay, so that took us a grand total of what? 2 seconds? All right, well, I'm going to show you guys another way to find the derivative today that takes quite a while. Now, so you guys are going to be tempted here to think, oh, why are we doing this? But remember, we're doing it, first of all, because what I'm doing here is why those shortcuts work. And so math is why things work. It's not just how things work, but also why. And then also in addition to that is the fact that you will see some questions where they actually are going to make it so that you have to know this process. So we need to know it, and it does take a little while, but usually, yes, anytime you're finding a derivative, we're just going to use the shortcut, obviously. But sometimes you're going to need to do this, so let's be aware of it. So if I want to use the limit definition of a derivative, that means they're asking me to do this. They're asking me to find the limit of my average rate of change, also known as the difference quotient, as delta x approaches 0, thereby resulting in the slope of a tangent line, which is also known as the derivative. Okay? So we're going to use that little formula there to get our answer. Now, here's how I like to start these problems off. I like to start off by finding this first. So let's do that. What is f of x plus delta x? Well, what this means is I'm going to take my function f of x, and I'm going to plug x plus delta x into it instead of just x. So my function is 2x plus 3. So I'm going to take my function, which is, let me start over here a little bit just so it doesn't talk my way through it. So what I'm going to do is I'm going to take my function, f of x is equal to 2x plus 3. And what I'm going to do is I'm going to plug x plus delta x into it. Just like that. And then I'm going to simplify it if I can. This side stays the same, but over here we can go ahead and distribute. So that's step 1, I'm going to call it. Find f of x plus delta x. All right, there's our step 1. Find f of x plus delta x. And basically you're just going to plug x plus delta x into the original function to do that. Okay, now that we have f of x plus delta x, what I'm going to do is I'm going to plug into our formula for the limit definition of a derivative. Plug it into the formula for the limit definition of a derivative. So here's how that's going to look. The limit as delta x approaches 0 of, and we're going to have one blank here, minus one blank here over delta x. Okay? Now what goes in the first blank there? Put my f prime over here as well, by the way. All right. So what goes in the first blank? Well, the first blank is f of x plus delta x, and that's what I just found in step 1. So I'm going to replace f of x plus delta x with what it equals, and that is 2x, oh, and I forgot to put a 2 here, plus 2 delta x plus 3. Next, I'm going to put f of x here, and f of x, that just means the original function. F of x is 2x plus 3. So I'm just going to put the original function right here. So I have f of x plus delta x here. I've got f of x here. All right. The next thing that we're going to do is we're going to simplify the expression. In the numerator. And usually that's going to require, like in this case, some form of distribution and combining of like terms. So let me show you what I mean there. In this case, I'm going to distribute that. And by the way, did you guys notice how I use parentheses here? I would highly encourage you guys to use parentheses. Otherwise, you're going to mess up on your distribution, or you'll be more likely to. So we have 2x plus 2 delta x plus 3. And then we're going to distribute. And after you distribute the negative, it becomes minus 2x minus 3. Now I'm not done simplifying because I can simplify a little bit more. As you guys can see, I've got a 2x and a negative 2x. Those can cancel each other out, right? I've also got a 3 and a negative 3. Those can cancel each other out. And just so you guys know, almost everything on this second half is going to cancel out something on this first half. That will almost happen every time. I'm pretty sure of it. And I just hesitate to say always, but I can't think of an example where it doesn't actually. So count on that happening. Everything over here will cancel with something over here. But because that side had a delta x, it has a little bit more. So now here's what we have left. On the top, I've got 2 delta x over delta x. Now, as you guys can see, and this was also true in the beginning, I just didn't do it there. But as you guys can see, I can't plug delta x, I can't plug 0 in right now, can I? If I plug 0 in, I'm going to get 0 in the denominator, and that's not allowed. But I can remove the discontinuity. Delta x and delta x cancel. Now, what is the limit of 2 as delta x approaches 0? Well, since there's no more delta x in here, I can't plug delta x in anywhere. So the answer is just going to be 2. And I forgot to bring down my derivative here every time. Let me redo that. All right. And so this just becomes 2 because you can't plug in the delta x anywhere, and we've got our answer. Now remember at the very beginning of the problem we did our shortcut that we learned back in chapter 1? Remember I said way up here when we had this, what's the derivative of this? And we knew the answer in 2 seconds was just 2, right? Well, we just went through a much more lengthy process to get the same exact answer. But I want you guys to understand, this is why that works. Okay, and by the way, I would add another step over here. After you remove the discontinuity, you should be able to evaluate the limit with some direct substitution. Okay, so there's our steps. All right, so step 1, find f of x plus delta x. Step 2, plug into your formula. Step 3, simplify. Step 4, remove the discontinuity. Step 5, direct sub, and you have your derivative. All right. So let's do an example that's a little bit like that for you guys now. Now I'm not going to write out the instructions. I'm just going to write out the function I want you guys to do. Okay. So there's that. Now, we're going to treat this one a little bit more like a guided practice real quick, just to make sure you guys, know how to do every step. So I want you guys to do step 1. Go ahead and pause the video here and do step 1. And when you unpause the video, you'll see the solution. All right, so step 1 was to find f of x plus delta x. You do that by taking your function and replacing the x's with x plus delta x. And if you do that, you get this. We do want to simplify it by distribution, though, after that, and we now have this. All right, let's go ahead and have you guys do step 2. So go ahead and pause the video here and do step 2. All right, so step 2 is to set up your limit definition of a derivative, and here it is. You should have put your f of x plus delta x here. You should have put your f of x here with a minus in between them, and then a delta x on the bottom. You have a limit on the left, and then you have your answer on the right, which is the derivative. And most importantly, well, not most importantly, but important, did you guys remember to use parentheses on those 2 expressions on the top? I would highly encourage you guys to do that. All right, let's go ahead and move on to step 3. I want you guys to go ahead and move on to step 3. Pause the video here and take us on over to step 3. All right, so step 3 is to simplify. So the first thing I would recommend doing is distributing the negative into this second set of parentheses, which makes them become positive 3 minus 5. And then these cancel, leaving me just with the negative 3 delta x on the top. All right, go ahead and pause the video here now and move on to step 4. Step 4 was to remove the discontinuity. Right now you can't plug 0 in for delta x because there's a 0 in the bottom and that's a discontinuity. But this discontinuity can be removed, leaving us with this now. And so now go ahead and do step 5, and when you unpause the video you'll see the final answer. And once again, like on my example, there's nowhere to plug 0 in for delta x, so since we can't plug it in, the answer is just going to be the constant there, which is negative 3. Okay, and so once again, we've used the limit definition to find the derivative of a function instead of our shortcut, which once again, the shortcut would be, we know right away that the slope would be negative 3 because the slope of this is negative 3 and the slope of this is 0. But there we have it. So let's go ahead and move on to another thing. For our next topic, I want to give you guys a shortcut for something here. All right, you're going to see this expression a lot, okay? When you're doing, well, not a lot, but you'll see it occasionally, and it's nice if you just have an answer already instead of having to work it out, okay? Now, there is a long way to work it out, and that would be using a FOIL method or a box method of some kind. I like to use the box. Now, you guys don't need to write this if you don't want to, but if I have x plus delta x squared, that means I have x plus delta x times x plus delta x. So we would FOIL that out, and we would get the following. That means x times delta x, right? All right, and then we have x squared. And then we have 2 of these, so that's going to be 2x times delta x. And then we have delta x squared. So this is really all you need to have written. We're going to be doing that every so often, and so it'll be nice not to have to do this every time. It'll be nice just to know what it equals right away to save us some trouble. Okay, so keep that in mind. Let's go ahead and see where we would have a problem that would require us to do that. So, example 3. I'm sorry, example 2. Let's say we have f of x. Matter of fact, I'm going to change it up a little bit. I'm going to say g of x because I want you guys to see it doesn't always have to be f. Let's say I have g of x is equal to x squared minus 3x. Matter of fact, let's say it's 2x squared minus 3x plus 1. And I want you guys to use the limit definition once again to find the derivative. Now, we could find the derivative really quick if I just wanted to use a shortcut, but we're going to use the limit definition of a derivative. All right, so step 1. What is step 1 again? Step 1 is where we take our function and we plug x plus delta x in for x. Okay? Now we're going to simplify that though. Now we did this on the last slide. So anytime you see one of those things being squared, you're going to want to have that. So here we go. We have 2, and then the x plus delta x squared we saw on the last slide just becomes x squared plus 2x times delta x plus delta x squared. The next thing I'm going to do is I'm going to distribute. So here I'm going to distribute a 2 into the parentheses. And here I'm going to distribute a negative 3 into the parentheses. All right, so there's that. So that's step 1. Let's go ahead and take a look at step 2. Step 2 is to use your limit definition of a derivative. So we're going to say, okay, the limit as delta x approaches 0 of, and we're going to need a lot of space here, because we know that our f of x plus delta x is really long. All right, my f of x plus delta x is this entire thing here. There's that. And then we're going to put the original function here. And the original function was 2x squared minus 3x plus 1. And that gives us our derivative. All right, so that's step 2, is to just plug everything into your difference quotient, or limit definition of a derivative. Now we're going to simplify. So I'm going to distribute the negative, and then I'm going to combine my like terms. Now, once you guys get a little bit better about this, as you practice, you don't have to show every single step. It's just that you got to be careful, because as you guys can see, there's a lot of stuff to write here, and so it's very easy to forget something. So you have to really take your time in writing this out and double checking what you're writing. I've already made 2 boo-boos, but I keep catching myself. Now there's so much to look at here, but remember what I told you? This kind of helps a little bit. Remember how I told you everything here should probably cancel with something over there? And it probably will. So let's start with the negative 1. Do you guys see a positive 1 somewhere? Yep. Those go away. Now let's move on to the 3x. Do you guys see a negative 3x somewhere? Boom, boom. And how about the negative 2x squared? Do you guys see a positive 2x squared somewhere? Boom, boom. All right. So if you just start on the right side, it's a little bit easier to find the stuff that you need to cancel out. I've been forgetting to put my delta there. And that's important because x and delta x are different things, right? X represents the starting point. Delta x represents the change. So you got to make sure you're using the symbols correctly. All right, thus ends step 3. That was step 3. All right, so step 3 was to simplify. So I distributed the negative, and then I combined my like terms. Now step 4 is to remove the discontinuity. Now I'm going to show you guys 2 ways to do this. The first way is the way that works all the time. The second way is a way that is a little bit faster, and that's kind of the way I'm going to prefer to go. So don't write this, I just want you guys to watch. All right, and then I'll just show you the fast way after this. So I want you guys to notice that, do you see how every term has a delta x in it? So what I can do is I could take a delta x out of that entire set up there. Just factor it out. Now, why would I do that? So I can do step 4, which is to remove that discontinuity. All right? But, as I said, I don't want to do it that way usually, even though that's technically a nice way to show your work. It just takes too long. So for me, I'm going to say, what you're going to do is this delta x on the bottom is just going to take 1 delta x out of all of these. So this is going to cancel 1 here. It's going to cancel that 2 and turn it into a 1, and it's going to cancel this out. And so what I'm going to be left with then is 4x plus delta x minus 3. So basically it just removes one delta x from the entire set. And that removes the discontinuity, because remember, at this point, we weren't allowed to plug 0 in because that makes the bottom 0. But now I've removed it, and I no longer have that on the bottom. All right, now here's where something a little different happens than the last ones that we were working on. Okay, here we actually have a place to plug our delta x in for, right? I could plug 0 in here. So if I plug in 0, basically you can just ignore that 0, right? And you just end up with this. And there's my final answer. Remember, so far in the other two problems, we just got a number. But that's because of the type of function we are working with. In this case, the answer is 4x minus 3. If I asked you to come up here and use the shortcut we learned back in chapter 1, take this and multiply it to the front, you get 4x. Derivative of that, minus 3. There's your answer. So we could use the shortcut, but once again, we need to know how to do this limit definition of a derivative. Okay? So there's that. So I'm going to give you guys a student practice this time, one that's a little bit like mine. I'll let you guys see how you do with it. So, as a matter of fact, I think I just realized that I have one little boo-boo here, and I don't know if you guys caught it, but I put f of x here. All of those were supposed to be g's. So we got to be careful. And that's why I wanted to include an example with a different letter, because I always want to emphasize the importance of making sure that you use the right letters. We get into a habit, I know I do, of using that letter repeatedly, F. But if you do that too much, you start to think that's all you're ever going to write, and it's not. All right, so here's your student practice. I'm going to give you guys f of x is equal to negative 3x squared plus 4. Go ahead and pause the video here, and this time I want you guys to do the whole problem. Okay, we're not going to do it step by step. I want you to do the whole problem. When you unpause it, you'll see the solution. Okay, so your final answer obviously should be negative 6x. We already know that because we could do the shortcut. So you know you should have ended up with negative 6x. So here's the steps. This is what I got for step 1. So check that on your slide. This is what I got for step 2. So check that on your work. And this is what I got for step 3 after I simplified. Okay. Step 4. After removing the discontinuity, this is what I got. And then in step 5, after you plug 0 in for delta x, you end up with negative 6x. Okay? Now I'm going to do one more type of problem just to kind of show you guys how to handle that situation because it's a little bit weird. And that will be it for today's lesson. Let's do one more example. And I'm not even going to have you guys do a student practice. I just want to show you guys one more problem. You will see a problem like this on your homework, though. Okay? Just want to get you guys exposed to it at least. So what if you have a weird function like this? Let's say I have h of x is equal to just a number like 5. Well, you guys already know that h prime is just going to be 0, right? So we know the answer is 0, but let's go ahead and use the limit definition of a derivative. So first of all, if I wanted to find the first step, which is plugging in x plus delta x, you'll notice there's nowhere to plug x in here. So x plus delta x is 5. Okay? You can't plug it in. So if I do the limit definition of my derivative, we have f of x plus delta x minus f of x over delta x, right? Well, in this case, we have 5 here, and we have 5 here. Now, there's my plug-in. Now let's simplify this a little bit. If I simplify this, 5 minus 5 is 0, right? So this was step 1, step 2, step 3. Now let's do step 4. Now step 4 is to remove the discontinuity, but you can't cancel out the delta x here. But you know what? It doesn't really matter because the top is 0. So how about before I make the mistake of trying to plug that into the bottom there, how about we just simplify this? Anytime you have 0 over anything, it's other than 0, of course, it's going to be 0. And so this whole thing here just becomes 0. So let's just do that. And therefore, the limit of 0 as x approaches 0 is, of course, going to be 0, because now we don't have to worry about plugging in a delta x because it's not even there anymore. And the answer is just 0. So we're all done there. Oh, and once again, I forgot my letters. This was supposed to be an H. Mr. Bailey. There we go. Okay. And there you guys have it. So that was the last example. We'll stop there, and we'll wish you guys well on your homework for this evening.